Okay, I think we'll get started. So today we're going to talk about periodic trends, and I'm going to let you learn most of this on your own. So there's a section in your book, probably chapter 6 or chapter 7, whatever book that you're using, that talks about periodic trends. And I would read that section and just try to get down the various things. So they'll talk about ionization energy, electron affinity. So learn what those things are and learn what their trends are across the table and down the table. So we're going to just focus on a few things today. I'll just pull out a few things and mainly focus on the reason for all of the trends, which is this idea of shielding an effective nuclear charge. So let's look at first just a couple of facts here. So a completely filled subshell is more stable than a partially filled subshell. And then half-filled subshells are relatively stable, nowhere near the level of a fully filled subshell, but they're relatively stable, and this is especially true for the Ds. So 5 electrons in a D is relatively more stable than, say, 4 or 6. Okay. So let's just look at the trends in the oxidation state as we go across the table. So the alkali metals are in the first column, right? And we've just said here that the full shell, so the noble gas side of things, is going to be the most stable. And this is the reason why noble gases neither want to give up electrons nor take on electrons, and therefore they're rarely involved in any kind of chemical reaction, which involves either giving up and receiving electrons fully and creating ionic compounds, or at least partially and creating covalent compounds. So they're rock solid stable. If we think about the alkali metals, if that loses one electron, then it has the same electron configuration as the previous noble gas, and thus it's it's much more stable than, say, if it were to lose 2 electrons. So we always see alkali metals with a +1 charge, or a 1+ oxidation state, because it's easy to lose the 1 electron, become 1+, but then it's harder to lose another electron. Now, you might say, okay, well, let's fill and make a -1 oxidation state, because then we'd at least fill that subshell, the S, which is true, you would fill it, but it is nowhere near as stable as losing an electron and creating the noble gas configuration, which is easy for it to do. So in nature, these will always be found as a 1+. Alkaline earth, okay, that's the next column over. So now to get to the noble gas configuration, then we want to lose 2 electrons. So these will always be a +2 oxidation state. Row 3, which would be like boron and aluminum groups, not row 3, column 3, 3A, that getting harder now because nature doesn't like to have these big negative charges localized on a small atom. But still, the common oxidation state there is 3+. Now, carbon, that can kind of go in either direction. We talked about this much earlier in the course. This is why carbon is such an important compound for life, because it can take on a lot of different oxidation states relatively easily and then get involved in all sorts of different chemistries. So the group 4, or carbons group silicon, that, yes, can go +4, can go -4, can go +2, -2 pretty easily, and even +3, -3. Oxygen group, that will tend to pick up 2 electrons. So if it picks up 2 electrons, get a 2- oxidation state, then we will end up with the noble gas configuration. Halogens, just one column over from the noble gas, very easy for them to pick up an electron and become negative. So those are pretty straightforward. The transition metals are a little different. When the electrons are filled in the transition metal, the spin pairing energy that we talked about last time on this 4s makes these very close. And in fact, it's often easier to lose these 4s electrons than to lose the d electrons. It kind of depends on the situation. Because of that, almost all transition metals will have a relatively stable, might not be their most stable, but a relatively stable +2 charge as an ion, or a 2+ oxidation state. And that's coming from losing the 4s electrons, which is relatively easy to do because of this, this spin pairing energy. Now, let's look at the case of iron. So iron will certainly have a +2. Now, its most stable state is a +3 charge. And what's happening here then is it's losing these 4s electrons, and then it's also losing this 6th electron, which is causing some spin pairing energy to happen here, getting us to then a very relatively stable, anyway, not very stable, but relatively stable half-filled D shell. So when we look in nature, the sort of the sink, what iron oxidation state wants to tend towards is the 3+, and then combined with oxygen, of course, we get that's normal rust, Fe2O3. But certainly there are a lot of compounds where that oxidation step is not complete. It's lost 2 electrons, and it's iron 2, a very common state. So as you look through the different oxidation states of the transition metals, see if you can now explain to yourself, in terms of losing electrons and trying to get to that noble gas configuration and half-filled D shell configurations, why the common oxidation states are the way they are. All right, now let's talk about the most important things today: shielding and effective nuclear charge. So when we look at any given element, there will be the inner core electrons, and then there'll be the valence electrons, those on the outside. So the valence electrons are the ones in the non-filled full shell. And so the inner core electrons would be up to that noble gas configuration, and then the valence would be any of those beyond that. The inner core electrons, as far as the valence electrons are concerned, so now we're looking at this from the point of view of the valence electrons. This charge, there's a lot of positive charge at this nucleus, but the inner core electrons shield that completely. So 1 for 1. So for every electron that's in the inner core, that will cancel out 1 proton in the nucleus as far as this one is concerned. So if there were only 1 valence electron, then and the rest were inner core, then the inner core would take care of all of would cancel out 1 for 1 protons, and there'd be just 1 proton left for a neutral atom, and the electron would feel exactly what it feels with hydrogen, 1 full positive charge. And we'd say the effective nuclear charge is 1. Right? So the nuclear charge could be, for the case of iron, for example, is 26, right? So we could have tons of protons in there, but the valence shell will not feel all of that because of the shielding by the inner core electrons. Now, we think, okay, let's add 1 more proton and 1 more electron. Yes, we go to now 2 additional plus charges because we're adding protons. The inner core shield 1 for 1, so there's 2 sort of exposed, and we have 2 electrons in the valence shell now. Now, what the electrons feel is not 2, right? They don't feel the full 2 charge because they're shielding each other. But they also don't feel just 1 because since they're both in the valence shell, they're not effectively shielding each other 100% each. And for S electrons, I think it's somewhere around 80% shielding. So the effective nuclear charge is less than 2, right? Less than 2, but more than 1. So it grows as we go across the row. So the effective nuclear charge, oh, I got this backwards. Effective nuclear charge goes up as we go across the table. So as we go across the table, the effective nuclear charge goes up, and that's because we're adding valence electrons. They're not shielding 100%, and therefore what each valence electron feels is a stronger charge than just one. Now, when we wrap around again to get to the next row on the periodic table, now all of those electrons become inner core electrons, and then it starts all over again. So there's a periodicity in the effective nuclear charge. Increasing effective nuclear charge, then it starts over at 1, increases, starts over at 1. All right, well, let's look at some of the consequences of this. And there's a very famous one with zirconium and hafnium, and the fact that if you look at the atomic radii for them, they're essentially the same. In some sources, you actually see hafnium a little bit bigger, other sources a little bit smaller, but essentially they're very close to one another. And we would definitely not expect that, because the periodic trend says that the radius gets bigger as we go down the table. And that's certainly true for cesium versus rubidium. Cesium is much bigger than rubidium. But let's see how this works. So we're going across this row in the periodic table. We hit zirconium. It has a certain effective nuclear charge. Couple of s electrons shielding each other. The p electrons are shielding. P's are pretty good shielders, almost as good as electrons. Then we get into the d. Then we get into the d shell, and the d's are actually very poor shielders, as are the f's. So we start to pick up effective nuclear charge very quickly across the d's, and we get all the way to xenon, and we have a pretty high effective nuclear charge. Now this wraps around and starts over again. Okay, and so, all right, that's good. This is much bigger than this. This is much bigger than this. Now what happens is we start to bring in the 4f electrons, and we drop down into the lanthanide series. So we have 14 more positive charges being added, all being shielded by f electrons, which are poor shielders. And so when we pop back out again, compared to zirconium, which there's no 3f's, so this just directly goes one more proton. Now we have 14 more and much less effective shielding. So the effective nuclear charge is much higher for hafnium than zirconium. And so here they're about the same, and then we're just on a larger shell. Here this is much more, so that sucks those electrons in, so much so that the radius of this is about the same. So those two atoms are about the same size. And that discrepancy, or that connection, holds across most of these, although this is where it's most noticeable, right here, right coming off of the F's. So that's a nice exception to know, or sort of exception to the periodic trend of increasing atomic radii, and you can understand that by our understanding of effective nuclear charge. So to summarize then, effective nuclear charge gets bigger as we go across because of the less efficient shielding of valence shell electrons. Then we come back, it's periodic, there's a periodicity. We come back because all those valence shells are now inner core for the next row, and it all starts over again. All right, so again, I'm not saying a ton of stuff on this area. Any chemistry book that you have will have a good chapter on this, or sections of the chapter. And so definitely take time, understand it, but really try to understand it from a chemical intuition rather than just a memory perspective.